Hello again. Tonight we're going to talk about the Vera C. Rubin Observatory and the LSST telescope slash camera that's inside of it, and why this particular astronomical facility is unlike others. So if you haven't heard about it already, the observatory has an 8.4-meter set of segmented mirror array at the back of it, and it's located in South America, in Chile, and it's at almost 9,000 feet up. So the air is rather thin, but you get clear skies. And Vera C. Rubin is the observatory facility. It's not specifically the telescope. The telescope, filters, camera was originally identified as the Large-aperture Synoptic Survey Telescope, or LSST, and so is the observatory. And then they commemorated the observatory to Vera Rubin. I won't say discovered, but realized that stars on the outer edges of galaxies move at an unexpected velocity closer to what's at the center. And so that's kind of like dark matter hauling the galaxy around, commemorated it to Vera. But the camera changed what the letters mean. It's now the Legacy Survey of Space and Time, which is still LSST. So you can't take the telescope or the camera out of the observatory. It's just all one thing. So I'll just refer to it as the Rubin. So how did this come about? Well, there is a part of the U.S. government called the National Science Foundation, or the NSF. This runs all of the U.S.'s scientific research labs. And there's another group called the Department of Energy. These are the people that work with particle accelerators and nuclear power, nuclear weapons, that kind of thing. But they also have a science office that does, non-militaristic kinds of things. And so the joining of the NSF with the DOE pushed forth the creation of the LSST. There was actually a group of universities and commercial folks that helped fund some of the interest in it, and it's called the LSST Discovery Alliance. And at the end of the presentation, there's links. But oddly enough, even though this is an astronomical observing facility, it's not in the NASA budget. It's in the NSF budget under the Department of Energy, but it's the Department of Energy's Office of Science. So once it's up and running, the actual operation of the observatory is through a group that's basically U.S. officiated astronomy observing technical operators, and that's AURA, NOIR, and NOAO. These are different organizations that focus on different things. Like NOIR focuses on obviously infrared, and the generic National Optical Astronomy Office, NOAO, they're more generic. But strangely enough, the front-end processing of the image data coming out of the camera goes through a facility known as SLAC. And this is associated with Stanford University, which is a member of AURA. But later on, why SLAC is there. So this is kind of a quick shot at the synopsis of the images that were released, if you didn't see them. So the image at the top is a composite of several images stitched together, and it's actually very large. It's a gigapixel size image, but I shrunk it down. And if you go in and look in very small areas of that image, you'll find like the image on the left, which is a star cluster. Sorry, the image in the center, which is a galaxy, and the image on the right, which is a nebula. So these are the kinds of things that the Rubin facility can image on a regular basis. So this is that same stitched together image. And if you're really clever, you can actually see a spot where they stitched it right in the center horizontally and just above vertical, the right edge of the tail of that fuzzy looking galaxy. You can see this little line. So it's not perfect stitching, it's computer-based stitching. But the majority of the things you see here, both the ones that look like galaxies and the ones that look like little red fuzzy things, well, those are all galaxies. And some of them are obviously elliptical galaxies. You can see the ellipses. Some of them are globulars. They're just like a ball of glowing mass, and those are stars. But it can stitch all these things together on a regular basis because it has its own supercomputing facility. The individual images have so many pixels in them, even your 4K or 8K or even 16K HDMI display would not be enough to do a one-for-one pixel to image pixel display. Scaling things up and down and cropping them and taking pieces out of them is going to be the norm for dealing with Rubin images. Rubin is also broad spectrum. This means it can see with filters associated with infrared, visible, the typical red, green, blue, and ultraviolet, or deep blue into ultraviolet, not deep ultraviolet, nor can it see in deep infrared, but it sees a wide enough swath beyond what human vision can see that it can actually show you blue stars, bright, short-lived blue stars in globular clusters, along with the longer-lived yellow ones, along with the even longer-lived red ones. You can actually see the variety of colors of stars in globular clusters. And it's very typical in amateur astronomy to focus on like one set of colors, like all the reds or all the blues, but Rubin, because it can take the same image and run different filters through them, it can actually give you this composite showing all the stars. So given the capabilities of the Rubin Observatory, it is a very fast optical telescope. It is, very short focal length. It is high light sensitivity, has lots of pixels in the camera, gigapixels. It does wide fields, more than a degree by a degree. Since it can shoot so fast and it can move so fast, it can capture squares of sky and do that on a high frequency basis and come back and hit the same area again just a couple of days later. And since it can see, and it's highly sensitive camera, can see in infrared, visible, and UV, all the images come in as grayscale and then they get put through the filter process. It was apt to see things that people don't normally think telescopes are good for observing. One set of observations took some folks by surprise and they had to go in and do some corrective action. If you have an optical telescope that can come back to the same area every 3 days and with high sensitivity, take a very large scale picture of that part of the sky in very high resolution, that means it can see asteroids and comets galore. All these little turquoise dots represent asteroids and comets. They're not turquoise. They're actually just sort of either whitish or reddish white dots, very small. But because they move, and they move every few days, and it takes an image every few days, it can actually see all of these asteroids and comets. And so far, they've detected over 1,000 of them in one of their gigapixel images. Given that it has IR, infrared sensitivity, it can not only see the sunlight reflecting off of these objects, it can also see the heat coming from these objects versus the cold of space. And it says asteroids and comets. It can actually see comets before they get close enough to the sun to actually create tails. So not only can it see asteroids and comets, it can also see satellites, not just our satellites, anybody's satellites, because it's looking out into space, and anything that goes by that light reflects off of, it can track it. Theirs, ours, corporations, it can see all the satellites. There's a slight problem with that. The US has clandestine satellites that are short-lived, like we, launch a satellite, go over and survey an area or listen in for some radio communications, and then the satellite deorbits. Those are not long duration enough orbits to let the world know where the satellite is. Rubin was showing off some of its work, and the US government, since remember Department of Energy, said, what are those? And they said, satellites. Anybody's satellites? Yeah, anything that flies over the observatory within the field of view, we can capture it. Here's the guy, contact him. And so the administrator of the Rubin contacted this guy and he said, we're going to arrange to put like a front end into your image processing. And we're going to need some office space, and it'll have a locked door on it. And so literally when the camera front end is gathering pixels, it'll go through this secret room, and whatever they want to take out, they can take out or mitigate, and then you'll get the rest of your data. Trust us. So the Stanford Linear Accelerator Complex folks came out and put in their upfront filter. There's a link to the article from the Atlantic in case you think I just believe in conspiracy theories. There's too much data coming in. There's going to be petabytes per day. And remember, you have megabytes, gigabytes, terabytes, petabytes, thousands of megabytes. That much data coming in, they have to scan it on the fly and archive it. There's no ability for a science team to go, could you point the telescope over here? We want to take a picture of this thing. That's what you would normally do. That's why Rubin is unlike the others. It's just going to scan the sky on a regular basis and produce data. And you can't say, I want you to point it here and take a picture. Now, I'm sure the Department of Energy can do so if they want to. They're the one funding it. But in general, it will just be taking a matrix of pictures across the sky, storing that in the archive, which is kind of a good thing, because if you think of something like the Hubble Space Telescope or the James Webb Space Telescope, there's a queue. If you want to use it for observing and you want to point at a particular target, you have to write up a proposal, and then you have to submit it, and then they review it, and then they talk to you about reviewing your proposal, and you could be told, no, our telescope's too valuable. You don't get to observe something that mundane. We're James Webb, go use Hubble. Or, we're Hubble. Why don't you pick some easy to access ground-based telescope? Okay, and they can do that. But that means that that science team loses out. And if it happens to be, some university students, they've lost their astrophysics observing work program. This is going to be different. You don't have to worry about proposals and slots and getting bumped from the queue at the last minute for whatever reason, or convincing, biased people that you'd really like to do observing. With the Rubin, it will just observe the sky on a regular basis. And if the target you want is either not in the archive just yet, or current picture is not in the archive at the moment, wait a little while. Every so often it'll come by and take another picture. And given how many years it takes to get a proposal successfully committed to like the JWST, your data will be available years faster with a lot less effort. So this is a different approach. This is why Rubin is not like the others. No proposals, no waiting in slots. But will the data be available? Well, you can go to the Rubin website right now, and there is an app and a web page called Sky Viewer. And they're taking the data that's been released, already been scoured by the government, has been released for people to use for science and just public curiosity. And so you can go use the Sky Viewer app or the Sky Viewer website, and you see the giant cursor there. When you move the cursor over the background sky, you can turn on an audio feature where it will play different sort of tinkling music sounds based upon what you're moving over. If it's a star or a globular cluster or a galaxy or whatever, it'll play different sounds, and you can adjust the audio amplitude. So that's one of these is not like the other. But here's the best part. Since the data is going to be publicly accessible, you don't have to commit to using the Rubin Observatory for your project. They're going to have a website referring to citizen science. And they're saying citizen, but it's really anybody. You can go and say, hey, I'm interested in looking at, T Corona Borealis or Betelgeuse. Give me an alert. I don't know if it's going to be email or to your mobile, but give me an alert if its brightness ever gets brighter. I'm looking forward to them getting the citizen science site working, and I'm going to put in requests. I probably won't beat the first people to it, but I'm going to see that there is a monitoring item for T Corona Borealis for the nova, and another one for Betelgeuse, the supernova. Because if the Rubin telescope is going by taking pictures all the time, it could be one of the first things to detect these nova and supernova events. And much like we recently saw a nova occur that we weren't anticipating, the Rubin not only can find asteroids and comets and satellites, it's most likely going to find novas and supernovas closer to when they start than just casual observing. So in summary, the Rubin is an observatory and the LSST is an instrument, and the operation of the observatory is unlike any other. Sure, they can put telescopes high on top of mountains in South America to get a clear, dark sky. Sure, they can make them large in diameter. They can have gigapixel imagers and stuff like that. They can be short focal length telescopes and shoot large parts of the sky on a regular basis. Telescopes can have infrared, visible, and UV filters. The new things that are different about Rubin is there's no targeted observing program. You don't have to file for anything. You don't have to get your time slot or wait in the queue, aside from stuff that the government wants to look at on the spot. But the public will have access to the instrument data minus the spy satellite. They're going to put up a citizen science site where average people can, sign up to say, hey, I want you to go looking for this. But I don't see any definition on that yet. So we'll see how that turns out. But the links are coming up. Do look at the links and look for the Rubin on the internet and look up as it looks up in the sky. So there's the observatory, the original LSST, the legacy terminology for it, the first look gallery in case you missed that, direct link to the Sky Viewer, and then the Rubin Citizen Science Center. It's not fully baked yet. It's sort of fledgling, but you can see where that's going to be. And then the people behind it all, I actually went out to Stanford one time and didn't actually get to see the linear accelerator, but I know where it is. The consortium, you can learn about the Discovery Alliance. Now remember, it's finding asteroids and comets, and some of those are going to be Earth orbit crossing or potentially hazardous. And the Rubin can relay its findings to the NASA Planetary Defense Coordination Office. This is the office at NASA that says, that one's going to hit us 50 years from now. That one's definitely not going to hit us. That one's 50-50. The Planetary Defense. I like the way Planetary Defense Coordination Office. And then what the National Optical Astronomy Observatory is, think Kitt Peak. I've been out to Kitt Peak. They have lots of telescopes there. And then the article about Rubin being a national security risk because it could show where short-lived clandestine satellites are in the sky, and the article in the Atlantic. So how many people didn't know about the Rubin Observatory?
I did never heard of it before.
Never heard of it before.
Never heard of it.
Never heard of it.
How many people had heard of Vera Rubin?
Yeah, she discovered dark energy, right? Or dark
It
matter.
was
Dark matter.
something in a newspaper lately.
Yes.
My husband told me, but I haven't seen it.
Yeah, she was the one that said there is an unseen force affecting the orbital velocity of stars on the outer edge of galaxies. And that's where dark matter came into play. They named it afterwards, but it was an unexplainable thing. But the observatory's been being built for better part of 10 years and designed a little earlier than that. There are other observatories being built, but the Rubin is the first of its kind where there's just so much data coming in that they'll store it. There's no time to analyze every grid of gigapixels. So they just store it. And then they put web front ends and app front ends on it. So you can go scour it if you want to look for something.
Was the government happy with what they said they were putting on the front end?
Yes, the government is happy with that because they get first dibs on all the data coming off the camera. And, they get the coordinates where it's pointed and those kind of things. And the U.S. National Reconnaissance Office that gets SpaceX to launch these things for like the CIA and the NSA, they know where that satellite is. They know what satellite that is. So if it's something they don't want to be in the archived data of the Rubin, they can either just wipe it out completely or they can bridge it out.
Now, looking at these blue dots again, trying to figure out.
They're blue. They're blue so that you can see them. Otherwise,
right,
they just show up like stars. They would be not spiky looking. They would just be little white, tiny white blobs. But if you look at an image and then you look at the same image 3 days later, where all those turquoise dots are things that are moving. And they're not moving all in one direction. They're moving in every direction.
So is the sky actually that full of, what are the blue dots representing again to make sure I'm looking at what
asteroids and comets.
Asteroids and comets.
Yes.
So is there that many asteroid and comets as the blue dots are? Or are they there because of the move? No, okay.
No. There were many more found just in the first observing from Rubin. And remember, the image that I was showing you is only about 3 degrees by 3 degrees, and the sky is 360 degrees by 90 degrees.
And that's like all the different areas you would see the same thing. You're saying, like if you pointed it or put it.
You would see asteroids and comets everywhere in the sky, not just there.
Because that isn't what we would have imagined.
No, we knew there might be thousands of them, but this is more like hundreds of thousands of them.
Yeah.
That we just had no ability to detect that they were there because we're staring at certain parts of the sky with a narrow field and taking images. And if we do that, it could go right by and then we're looking over here. And then the next one goes right by and we're looking over there. This is like giant field of view. Quickly take a snapshot, come back 3 days later, take a snapshot of the same part of the sky. Look how many things moved in different directions.
Excuse me. Oh my gosh. Then this just came out. This information is new.
It was publicly released this week, but it's been known about for, I don't know, 6 months.
Oh, so it's new. Yeah.
Relatively new. But when you show it to an astronomer, their first thought is, how do we get rid of all those satellites? There's more asteroids and comets than there are satellites.
Yeah. So what is being represented for the satellites there? Is that the purple dots or the pink dots or some other dots?
It's not in that image. Remember the image that was the square that had the little white streaks on it?
Yes.
That's the satellites.
But there's satellites in this picture, right?
Yes. They did not highlight the satellites. They only highlighted the asteroids and comets.
Oh, okay. So I'm looking for something that's not there to see.
Yeah. Well,
they're there, but you can't see them.
Yeah, the asteroids and comets move very much faster than the satellites move very much faster than the asteroids and comets. The asteroids and comets look like dots because you're only looking at them every 3 days. Whereas the satellites, if it takes you 5 seconds to take a picture, you're going to get a streak. You're not going to get a dot.
Okay, so now we're seeing some stars in this picture.
Oh, yeah.
With the asteroids. And what are the purple dots? Do we know? Because there's a couple purple, couple red.
Let me back. Oh, you're looking in the PDF. Let me back up.
Yeah. Well, I think it's a beautiful picture, one. But
the blue dots.
Blue dots, yeah, that one.
In this one, all the turquoise things are comets and asteroids.
And this is a real picture?
Yes, it's not an artist rendering. The artist
goodness.
The artist rendering part is the turquoise dots.
Oh.
If you remove the turquoise dots, what's beneath the turquoise dots would be little white dots or little reddish dots.
And they made them all blue.
So you'd see them. Look how many of them are there.
Yes.
If you said, what do they look like underneath the turquoise dots? If you look right in the center and you see that group of 3 that are really close together, okay, down below to the left of it, you'll see an elliptical galaxy. And then if you look up and to the left of it, you'll see a little white dot. And then you look to the right and you see an even tinier white dot. The individual asteroids and comets would look like those little tiny white dots.
Okay.
But if you look 3 days later, they would move and they would all be moving in different directions.
And is that they're white still because that's the first time they're getting their picture taken? They haven't moved?
Oh, no, that's a star. That one's a star. That's why it's not covered by a turquoise dot.
But I meant the other white little things that you were saying to look at.
Those are stars and galaxies.
Oh, okay. And the pink dots or the red dots?
The big blobby looking things, those are spherical galaxies. And the elliptical orangey looking things, those are elliptical galaxies or spirals. And then the red and the orange things towards the lower right, those are stars in our galaxy.
Oh, well, it's sort of nice to know it's a real picture. And that we're really seeing all that really.
and the other thing you didn't mention is you see the grid, the gray horizontal lines. Those are so they can identify the coordinates of things. That's not actually in the sky either.
But you can't tell distance.
Oh, well, I knew that. That's why
I know, but you know, I have to poke fun because people will say like, so the Earth globe, does it have all those lines all over it? What are you talking
That was one thing I didn't ask. I knew.
I have had people ask me, do those lines go over the water too? Like, no.
No, I was just noticing about there's no distance way to tell.
No. The only way you can tell distance is by, if you know what the thing is and you know how bright it is, then you can judge how far away it might be. That's one of the stellar stepping stones that we can use to judge distance. For the things that are in our galaxy, those are very much closer. And the way you judge their distance is through something called parallax, which is if in January I look at a particular field of stars, and then in June I look at the same field of stars, things will move. It's like left eye, right eye movement. And now from that triangle, I can judge how far away that object is. It's called parallax.
So this Rubin is earning its keep, hey? I mean, it really surprised people.
It surprised a lot of different people in a lot of different ways. Yes, the asteroids and comets, it found them so easily and in such huge quantities, well beyond what the NASA Planetary Defense Office had already seen. And they're like, how do we get in on that? So there's a linkage between the Rubin's observations of asteroids and comets and the NASA Planetary Defense Office, because they've got a lot more things to catalog now.
This is all over the United States. The sky is over the United States.
No,
right?
No,
or where?
No, the observatory is in South America.
Oh, okay. So where is it showing? So it's over South America, or is it part of the United States? Or
think of it as the telescope is located in South America.
Right.
It's on an altitude azimuth mechanism, which means it can point 360 degrees around from 0, which is the horizon, up to 90 degrees, which is zenith. It can see whatever it can see from its location in South America, which means it cannot see the entire sky.
Right.
It can only see up to where the horizon gets in the way.
Right.
It's not moving.
So where's the horizon on this? I mean, like, can they see anything in our sky or not?
They can see things that are in our sky, but only from like 90 degrees on the horizon, because they have to, because North America is north of South America. So if you wanted to see exactly what's in the sky over North America right now, you'd have to have the Rubin point down towards the horizon. But it can do that.
Oh, okay. That's pretty cool, isn't it?
Well, when you're up that high on a mountain, think of yourself as you're very elevated. And when you point down to 0 degrees, you're not looking down to the actual horizon because you're up on a mountain. Your horizon is much lower. So when it's pointing at 0 degrees, that's much higher up in the sky than the horizon would actually be.
Now, you have told us when we look at satellites that we put up there that are man-made, and they are all close together. You say, Joanne, don't worry about it. There's so much space in between them. They're not going to clash with anything. Is that the same thing with this picture?
Yes, the same thing holds true for asteroids and comets. If they were going to run into each other, they would have done so millions of years ago and already settled out all those movements. There is, certainly hundreds of thousands, if not millions of miles between each one of these things. Depth. Space is 3D. It's not flat. It's not like in Star Wars where you got to do dodge them between the asteroids.
But there's plenty of them there. Surely we will have to dodge something.
Big. It's not only large spherically, it's large depth. It's larger in depth than it is spherically.
But we would have been surprised to find that many up there if we didn't have this showing us this now.
Correct. They knew it might find some, but to find over 1,000 in the first large-scale image they took, and that's only like a 3 degree by 3 degree piece of the sky. Yeah, it's going to find a lot of asteroids and comets that we didn't even know were there.
And I don't know why I'm surprised, because I thought the James Webb that went out there was looking for things like this, but it's not.
No, it's not. The Webb telescope has a narrow field of view, so it looks at a specific target. Like if it wanted to, it could look at that galaxy just above center, but it couldn't see the rest of the sky at the same time. So it's got a very narrow focus. So you have to submit a proposal. I want to use the Webb telescope to look at this at this time of the year. With the Rubin, it's just like, every 3 days we're going to come back and hit the same spot. So just go to the database and look at the data.
Quite amazing.
Yeah, that's why it's unlike others. This is a new approach to doing astronomy. Given how much success they've had so far, it could be like the next way we do things. One of the oddities is if you have a telescope that has a very long focal length and you need to stabilize the sky using like lasers reflecting off the bottom of the turbulent atmosphere, and then you dimple the mirrors or something. You can do that with other telescopes. You can't do that with the Rubin because it shoots the image so fast that you couldn't get the deflection to correct itself in the time it took to take the picture. The second thing is it's shooting like individual panels of a degree by a degree for making a composite that's like 3 degrees by 3 degrees. And that much sky area is going to have so much distortion. It's much better to have a faster optical telescope and just shoot faster before the sky can wiggle, unlike others.
Now, people will look at this and say, hey, I have more to worry about with asteroids and comets than I thought I did.
What you don't know typically won't hurt you.
Yeah, but now I know.
The second thing is, if it's really got your number, if it's really lined up with the Earth and it's going to be a planetary killer, at the moment, our technology has no ability to do anything about it. So what's that 3-body problem on the streaming show? If you see it coming,
You dig a hole.
dig a hole, or as the saying goes, kiss your tuchus goodbye.
Yeah.
Any other comments or questions before I stop recording? Okay, hearing nothing.